right, I think we will go ahead and get started again. So before lunch, we were talking about stuff that, tools that come almost entirely from the machine learning literature. So I tried to show you economic applications of them, but if you want to go back, understand those tools, do some of the original readings, you'll be reading things in machine learning proceedings. And now I want to shift gears and assume that, we've mastered whatever machine learning we know to be able to extract our structured information from our unstructured data, so from our text or images, and now we're ready to do our usual economic stuff with them. But having extracted them, we understand that what we have is not the truth in some sense, that it's measured with error. Probably even the best deep neural network model is going to make some mistakes, and we want to take that seriously, or we want to know, do we need to take that seriously? And the answer is going to be yes. And so I'm going to shift now to talking about econometrics. And I will talk a little bit about some work that's been done in the statistics literature, but by and large, kind of the punchline of the next discussion is going to be that actually econometric tools that we've actually had since the 1970s, we can take those and we can apply those to predictions from deep neural networks. And there's some things to be aware of. But basically, our traditional econometric methods work in order to ensure unbiased, robust, efficient inference with unstructured data. All right. And so this talk that I'm going to be giving over the next few minutes is based on work with Jake Carlson. Jake is a PhD student at Harvard. He's an econometrician, a really fantastic econometrician. He's only going into his 4th year, so he won't be on the job market for a while, but he's definitely someone to watch for. All right, so to kind of step back and recap our motivation from this earlier today, stated slightly differently. So we want to use unstructured data in our research. We can't use it directly. It's high dimensional. It's complex. We can't interpret it in its raw form. And so instead, our goal is to extract low dimensional information from that unstructured data. And kind of in the language of machine learning, this is referred to as structured data. And structured data is low dimensional. It's interpretable. We can take it and we can plug it into whatever statistical analysis that we want to run. And so there's a really, really long history of using unstructured data in economics. And so if you think about things like institutions, polity uses text in part to measure institutions. Kind of any conflict data set, most of those are based on newspaper and other texts. Political stability, policy uncertainty, violence, all of these are extracted from text. Economists have been studying these things for a long time, long before there was deep learning. We also try to derive things like sentiment or topics or other structured features from government transcripts, from corporate filings, earnings calls, patents, web texts. Satellite imagery is used to measure economic activity, economic development, urbanization, particularly in places where we don't have a lot of great higher frequency economic data. And remote sensing data supplements sparse ground measurements of temperature, precipitation, pollution, agricultural, land use, illicit activities, deforestation. The list goes on. And so in short, using unstructured data in economic analyses is not a new thing. But what is new is traditionally, it would be really costly to extract structured information from these data sets. And so typically it was some large-scale external initiative that extracted the data. So you have like PRIO conflict data. They don't really share their methodology. Somehow they extract conflict from newspaper articles. We don't know how they do it. It's probably humans reading the article, but we don't know exactly. And that's just what there is. If you wanted to use that information, you use the data sets that are typically kind of constructed by some large-scale external initiative. But advances in computing and deep learning have drastically reduced the costs of being able to extract structured information from text and images at scale. And so it's become super common for economists actually to create our own data sets, to start with our own 100 million newspaper articles and extract our own information from those. And economists have done this in different ways. Traditionally we might have looked for certain keywords. And by the way, everything I'm going to say today applies to that technology as well. But deep neural networks are the state-of-the-art tool for large-scale features extraction from unstructured data. And we kind of typically assume that if you're doing research today and you're trying to extract information from text or from images, you're probably going to be using a deep neural network, or at least maybe you should be. All right. So neural networks will not generically produce unbiased predictions in finite samples. And the measurement error that comes out of a neural network, there's really no conceivable scenario under which we would expect that measurement error to be classical. So you have to make choices as the researcher about what type of neural network architecture you're going to use. The distribution of your training data, what type of data is that neural network going to see? You have to make lots of implementation details about your hyperparameters, and all of those can introduce systematic biases. Even leaving all of that aside, the fact that we have nonlinear transformation at each layer of the neural network and the frequent application of neural networks to binary or multi-class classification, that alone violates the assumptions that are required to have classical measurement error. And so basically, if there's measurement error in our neural network, there's kind of no reason why we would be able to assume that it's classical and that we can just ignore it. And any biases in the predictions that you make with a neural network, sort of in your first step of your estimation, where you're predicting your structured data, any of those biases will propagate to estimators that rely on those predictions, and that's going to affect both your point estimates as well as uncertainty quantification. So if you have a large data set, sampling variation is likely to be very small, but if you have a poorly performing first step predictor, so in other words, if the neural network that you're using to predict your structured data in the first step, if that's not very good, that can introduce an enormous amount of uncertainty if you take that into account. And so really, like if you ignore that, you're going to make very confident predictions, but if you take into account that your neural network is not making very good predictions, there's actually going to be an enormous amount of uncertainty about what we can actually learn from that data that you extracted. And I'd say that concerns about imputation bias from neural networks, so bias from imputing that structured data, are further heightened by the availability of off-the-shelf neural networks that are very cheap to implement. And so you could easily say, okay, I'm going to make predictions with, GPT-4o mini, with Claude, with another version of GPT, with Gemini 2.0 Pro, and the list goes on. There's so many different off-the-shelf neural networks that you can just use, and that raises concerns that people might go and p-hack with that. I'm going to see what it looks like with Gemini and with 4o mini, and I'm going to choose the one I like best. And hopefully nobody's doing that, but we don't want to have to assume good intentions. We want a way to be able to take kind of that bias seriously, so that once you correct your standard errors and your point estimates for the bias in your predictions, GPT and Gemini will give you the same answer.
Yes, there's also another related problem, which in some sense the neural network is developing a model of the data in order to reduce its dimensions down to this lower dimensional representation. So if they then take an economic model and estimate it with the data generated by the neural network, is sort of, I may just be testing whether my economic model represents the model of the neural network very well, rather than the sort of model of the data from which
yeah.
it's the raw. In some sense, the neural network is just a form of the model. In some sense, if literally it was using a log linear model and I estimate a log linear model, then that's going to provide a good fit to the neural network, but might not represent the raw and structured data well.
Yeah, absolutely. Yeah, that's a great point. I completely agree. All right, and so in short, hopefully we're on the same page. I will say, I think right now, neural networks are the new hot thing. There's a rush to get out papers, and I mean, there's a lot of papers where people, shockingly enough, there's not even any test set, nothing. Forget trying to correct the bias. We don't even know how well this thing is doing. So part of what I want to do is just to convey, we have to take this seriously. And as I mentioned this morning, Sendil, Ashish, other co-authors of theirs, also have done a lot of great work showing that we can't assume that these models are going to be accurate. Humans are really bad. Economists maybe even are really bad at predicting when they're going to work well and when they're not. So absolutely we need a test set to see how the models are doing, but we're going to take that a step further now and say, not just should you have a test set, to see how well we're doing, because we could sit here and argue all day. You have a classification problem. The F1 is 0.8. F1 is a harmonic mean between recall and precision that's used to evaluate classification models. We could sit here and argue all day, is that good enough or not? There's not an answer to that question unless we take into account in a principled way how that bias propagates into the estimates that we want to use those predictions for. A related point is if you're not very happy with your neural network predictions, there's investments that you can make to make them better. So for instance, you could train a larger model, which will be kind of more finicky to train, more costly to run, but it will work better. You could collect more training data. You could collect higher quality training data. You could just train for longer on that additional data. You could keep refining your implementation details. These are all investments that we can make, but they're costly. And so how do I know how good is good enough? And the answer to that question, is going to depend on how the bias from my imperfect neural network propagates to point estimates and uncertainty quantification and whatever I ultimately care about estimating. So here, we're taking the perspective. What you care about at the end of the day is not how accurate your neural network is. What you care about at the end of the day is some quantity of interest, an economic quantity of interest that you're trying to estimate with the data. And so we want to be able to actually quantify how that bias propagates so we can know, is this good enough, or do I need to keep on making more costly investments, sitting there all day labeling data when my RA won't do a good job of it, or whatever those costly investments might be. Not talking personally about anybody, but. All right, and so in order to address these challenges, Jake and I developed a framework that we call MARS, which stands for Missing at Random Structured Data. MARS provides a framework that we can use to conduct valid, efficient, and robust inference, and I'll talk about what we mean by all of those terms in a little bit, on estimates that incorporate unstructured data through their low-dimensional features, which is a fancy way to say we're going to use unstructured data in our analyses. We can't use it directly, and so first of all, we're going to impute that low-dimensional structured data, probably with a neural network, although everything in this framework would apply to kind of other ways of imputing that as well. And so we're going to frame, as the name suggests, inference with unstructured data as a missing data problem. Because our raw unstructured data sets typically lack the low-dimensional summaries that are relevant for our analyses. So I think I gave the example this morning. We want to know if this newspaper article talks about economic policy uncertainty, but the author didn't start the article by saying this talks about economic policy uncertainty. We have to impute that. And that data is missing because it would be super costly for me to go through and do it all by hand. I have 50 million articles. That's completely infeasible. We clearly need some kind of imputation technology to impute that missing information, and that technology in today's world is going to be a deep transformer-based neural network. And so as the name suggests, this framework builds upon Rubin's classic 1976 missing at random mechanism. So this is essentially taking missing at random, which by the way is also a foundation for causal inference, and applying it to deep neural networks. Yes?
Are you thinking of a setup where ground truth exists?
Yes.
Okay, so
Yes.
you're assuming that this is a classification
Yes.
problem. You and I would not disagree what the classification is.
Exactly. So there's some ground truth. We might disagree, and that's okay, but you're willing to take a stand. So I don't think it's truth in some deep sense, but you're willing to take a stand that I've measured this. This is what I mean. This is what I define as economic policy uncertainty. This is reasonable, and I'm going to have, my validation data that I'll stand up for. So I may disagree. I can think economic policy uncertainty is something different, and that's fine. I think we're not trying to get truth in some deep sense there will be valid inference for your definition of economic policy uncertainty. If that definition is nonsensical, then like you've just studied something nonsensical, but you are at least willing to take a stand. This is what I want to extract, and I'm able to extract it. And I think that's, I think that perspective is helpful even for complicated things like economic policy uncertainty. I mean, we could argue about what that exactly means, how it manifests in newspaper articles, but kind of at least once you've taken a stand, which by the way, in that paper they do, they have a long appendix and they state this is exactly our definition of it, this is how we trained our RAs to do our audit sample. Like, once you take a stand on it, then at least we can have a debate about what it means, whereas when people kind of don't want to take a stand on what they're trying to measure, then I think it's harder to make progress. All right. So our goal is to take foundational results from semi-parametric inference with missing data and use this to debias estimators that use predictions from deep neural networks. And so the key idea is to collect a validation sample that contains ground truth values, which, as I just said, doesn't have to be truth in some deep sense, but you as the researcher are willing to take a stand. This is what I'm trying to measure. And you're able to do that. And you use this sample to estimate the bias in the imputed data and then adjust your estimates accordingly. All right, and so I think, I just largely discussed this, but what do we mean when we say ground truth? Not truth in some deep sense, which may be unattainable, for some of the things we want to measure, but rather ground truth is obtained through some costly process. Typically that would be annotation by a highly skilled and motivated human expert. In the remote sensing world, it might be ground station data, which is where the term ground truth comes from. In some contexts, we might think it's a very expensive, neural network, and you believe that's going to give you the truth. But even in that case, typically it would be good to have a human back that up. And so neural networks, from an econometric standpoint, they're going to be treated as a black box. I mean, we have no way to characterize, to say the convergence rate of a transformer. That's just well beyond kind of what we can do because this is such a complicated object. So really to make, some people are thinking about, characterizing simple, two-layer neural networks or whatnot, but it's very complicated. We're not going to make progress at this point in time given the state of our knowledge and, characterizing formally a transformer. So we want to treat it as a black box, and we're going to treat it as a black box. But it's not a complete black box because the outputs that come out of that transformer neural network have to be interpretable because you have a clear implementable procedure for measuring what you want to extract, for measuring your ground truth. And so that's what ground truth means. I can hate your definition of it, but you have a coherent definition that can be applied, and then you can have valid estimates for what you are trying to measure. Yes?
The validation sample should be different from any training sample.
Yes.
In the sense that it's completely separate, it's not being fed into the machine learning model, so that otherwise kind of overfitting might occur.
Exactly, yeah, exactly. And so what you do is, you have labeled data, and then you're going to do sample splitting. Yeah, and you don't use that. You don't use that data to train. You don't use it also in your kind of inference sample to compute your estimates. This is data held apart that's used just for correcting for the bias. And the key thing is that this validation sample must meet the missing at random assumption, which says that after adjusting for anything you can observe, annotated data, so the data you've labeled, and unannotated data, the data that you haven't labeled, should be comparable in their ground truth values. And so this is basically saying you have your labeled data conditional on observables is a representative sample. And this parallels the selection on observables assumption in causal inference. Causal inference is a missing data problem because you're missing, control observations for treatment and vice versa. And so basically everything we do is going to parallel causal inference, which I think is nice because it makes it more intuitive. But in short, you need a representative sample of labeled data. And why? Like, why is this so important? I mean, it's so important. We named the framework name Missing at Random, after Rubin, who also named it that because it's very important. And so if you do not have a representative sample of ground truth data after you adjust for observables, if you have a non-representative sample, you just have no information to correct sort of the biases in your unlabeled data that don't look like your labeled data because you don't have representative data. And so you'd have to make assumptions, right? You'd have to assume, oh, well, the bias of this neural network in my labeled data looks the same as the bias in my unlabeled data. And you really don't want to do that in the case of neural networks because there's a huge literature showing that assumption is usually not going to be valid. For instance, maybe you don't have labeled data for a subset of observations because it's very difficult to get data for them. Well, your model is going to be trained on data that looks like, data that's easy to get, right? And so we'd expect it, and there's a huge literature that shows that it would do worse on that data that looks very different from its training data that's difficult to get. So in short, I think economists, sometimes we're just comfortable making assumptions like this, and maybe sometimes it really is the best you can do, but we really don't want to make strong assumptions on the form of the bias from the neural network because we cannot characterize that. It's too complicated of an object, and we have plenty of reason to think that this bias is very complicated, and so we'd rather just have a representative sample and be able to measure it and avoid those assumptions. And by the way, in a world where researchers are increasingly creating their own data sets from text and from images, this is quite feasible because you're the one who's choosing how to annotate data, and it doesn't have to be completely random. It can be based on observables, stratified sampling, and we'll talk more about how you collect this data and things like unbalanced data sets. But in short, this assumption is feasible in a world where you are the one putting together the data. Okay, I think I kind of largely went over this, but there are some situations where the entire reason why you want to use a neural network is that you have no ground truth and you cannot have ground truth for some subset of observations. And so like imagine, you want to predict famine in a conflict zone. There's no way to get on the ground to collect ground measurements. And so you're going to use satellite data. And there's just no ground truth because that's the entire reason why you're using satellite data. And people have thought about this problem. In general, you just have to assume that the form of the bias is the same as the sample for which you have ground truth data. There's a big remote sensing literature that says not to do that, by the way. But sometimes it is the best that you can do. And I think you just have to own, like, OK, this is a proxy. I don't really know what crop output in South Sudan looks like, but hey, we need to predict whether there's going to be a famine, and this is the best we can do. It's an important question, and so I'm going to proxy. And I have no problem with that. Like, if you don't have ground truth data and you can't have ground truth data, and you say, okay, well, like this is a proxy, then that's I think that's fine because then at least we're having kind of a honest conversation that I don't know what the bias in this thing is. I'm not treating it as the truth. But if you want to treat it as the truth, I would encourage having that representative ground truth data. And so Mars directly addresses this kind of fundamental limitation of neural networks, which is that they have this bias that shifts in complex ways with the training data and how that interacts with what you're feeding into it, and is too complicated to characterize. We're addressing that limitation by having a representative sample of how the neural network is performing. All right. And so there's an entire literature on debiasing with a ground truth annotation sample. So there's been a big literature in statistics, mostly under the heading of prediction-powered inference. There's other work, Agami et al. Sindel has kind of an applied framework. And so I would say that the contribution of this paper to this literature is threefold. So first of all, we develop a theoretical framework that unifies this work and links it back to much older familiar problems, such as causal inference. I'd say that the approach in the statistics literature is you start with one paper, and that assumes everything that happens in reality away, but you have your simple framework. And then you write another paper that takes into account this one complication, and then you write like a third paper that takes into account this other complication, but it doesn't put them all together. And I think that's like a valid way to write papers, and it's maybe more common, but in econometrics, we tend to like the framework that incorporates everything. And I think in this case, it's actually kind of fairly intelligible to people because it's based on econometrics that we've been doing for like 50 years. All right, and so the second contribution is to identify estimators that are both unbiased and efficient. So the existing literature kind of overwhelmingly doesn't worry about efficiency. Like we like efficient estimators because I feel like, you know, economists are never that well powered. And so efficiency is very helpful. And then finally, you know, a central part of the motivation for working on this is that there's a wide variety of settings that come up in economics that this existing literature does not address. And so I just wanted to debias some of my estimators, and I couldn't do that because they weren't, you know, the scenarios that come up a lot in economics weren't addressed by this existing literature. And so our goal is to make it feasible and easy, you know, for researchers to apply debiasing to a wide variety of settings.
I was just sort of wondering about the relationship to specification searches. So I guess here you have in mind, I know the model I want to estimate, and I want to know, am I going to get a biased and efficient estimate of this particular parameter in this model? I guess in the background is potentially also a kind of model specification search, right? So maybe the model I'm considering is not really the right model. Maybe I kind of overfit in my training sample. Another reason for having an extra kind of set of data set aside could be for sort of specification testing. I just wondered what your thought is on that and how you see this as being related to that separate issue.
Yeah, I think that that's something that I hadn't really thought about. But I mean, I think that you're right that you know, I guess it depends. If we're talking about kind of specification search for the neural network, right? In this case, it shouldn't matter kind of what neural network you use. You should get valid estimates, unbiased estimates. Now, if the neural network is really bad, and the confidence intervals will be really large. And I'll show you some empirical examples of this where we try kind of using different neural networks to predict the same thing, and some of them are really bad, and then they can range up to being really good, and like they all kind of, as we would expect, give the same answer, but same can be like huge confidence intervals, right? If you've found a model that's not very good. I mean, if in terms of how this interacts with, you know, specification search for your kind of statistical, your econometric model that you want to use the data in, I mean, I haven't really thought about that. So in everything I do today, we're going to assume that if you hadn't imputed the data, you know, if you hadn't imputed that data with a neural network, if you just had the ground truth structured data, then your estimates would be identified. You know, so we're ignoring any other, you know, of the myriad of complications that come up with identification to just focus on this one problem. You would have identification if you had, you know, your definition of the ground truth, but you don't have that. You're imputing that, and so kind of we're just focusing along that single dimension. All right. All right, so you know, from a theoretical perspective, we provide a framework that unifies recent literature on doing inference with black box AI models. So when I say black box, I mean we're not gonna try to characterize anything about the transformer because we basically can't. And so we're gonna integrate that literature, which was largely developed across disciplines that don't really talk to each other, and it doesn't really cite each other by and large. Especially not at first. And then we're going to integrate that with some older literatures. So first of all, there's an econometrics literature on measurement error, which is probably the most closely related to what we're doing because this is ultimately a measurement error problem. It's a measurement error created by this complicated thing, the neural network, but at the end of the day, it's a measurement error problem. We're going to relate this as well to widely used inference methods that incorporate machine learning-based first steps. So the debiased machine learning. Basically, you can show that our framework is equivalent to debiased machine learning, but in debiased machine learning, they're solving a very different type of problem. And then finally, 2 classical literatures on missing data and causal inference. So it's kind of interesting. I was talking a bit to Whitney Newey about this, and he said, like, Robbins, who's one of the main guys who did this classic literature on missing data, initially he had written a paper about causal inference, and the statisticians didn't like it. Like, they're like, causal inference isn't interesting. This is something that, you know, just biologists do in their clinical trials. It's not an interesting statistical problem. And then so he just turned it into missing data, and like people thought it was really interesting because it's more general. But we're going to see all those connections to causal inference because causal inference is a missing data problem. And so like in our framework, there's going to be kind of an exact sort of parallel to what you need for causal inference. I think that that's helpful. You know, I had somebody tell me, you know, we're engaged in a debate, you know, at my university about whether we need to teach econometrics differently now that machine learning is here. Do we need a totally new econometrics? And I think, you know, there's a strong, like, the answer is no. I mean, there might be new problems that we've never thought about, like, and we have to kind of think about them, but at least from the standpoint of unstructured data, like, we already know how to think about this, essentially. And so I think, like, that's a punchline. All right. Okay, so efficiency. So most of the existing work on using predictions from black box AI, they don't talk about efficiency at all. You need to take a semi-parametric approach to think about efficiency, and they don't do that. Like, one of the papers is like, oh, this is too complicated. But we think that economists, like, we're used to semi-parametric inference, and so hopefully I'm not saying anything that's too complicated. And so for an estimator to achieve asymptotic efficiency, we show that the imputation of missing structured data should depend not only on the unstructured data, so like your text or your images, but also on context-specific structured variables that help to estimate your target parameter. And so let's say you're going to use the missing structured data as your instrument, and you have some controls in your regression that are not orthogonal to your instrument, like, then you would want to use those controls to help predict the missing structured data. This is something called deep and wide learning, where you use kind of both the deep learning, but you incorporate structured data. You know, so you don't have to do this, right? And if you didn't do this, you did the simple thing, your estimates would still be unbiased. But to achieve efficiency, you would want to do that, which I think is interesting and something that hasn't been really pointed out. And then finally, as I said, a key motivation for this is just to make it much easier for researchers to do unbiased inference in practice. And so we derive robust and efficient estimators for descriptive moments, linear regression, treatment effects identified through linear IV models, modern differences in differences, and regression discontinuity. And so that's essentially like some of the, you know, most commonly used estimators. And because we take this semi-parametric approach, it would be relatively straightforward to integrate this with recent advances in automatic debiasing, work by Chernozhukov et al., which then would allow you to extend this framework to kind of much more complicated estimators. All right. We also handle a few key extensions. And so one thing that really motivated me to think about this is in economics, it's almost always the case that we're probably not running our regression at the level of our unstructured data. And so let's say that we have, you know, 50 million newspaper articles, but our goal is to predict economic policy uncertainty in the US in 1997, and we're running the regression at that level. And so existing work on debiasing, none of it applies to that problem because it's all going to assume that you have ground truth at the level kind of at which you're running your downstream regression. And, you know, we could label all 50 million articles, but that's not feasible. Even if we did that, in some sense, economic policy uncertainty in the US in 1997 is a population level quantity, and there is no measure of it in finite samples, right? At best, we have our kind of sample of newspaper articles. you could take a random sample, but let's say in that paper, right, they always take the log of economic policy uncertainty, they interact it with things, and so you can't just do that either. And so we're going to develop a framework for using aggregated structured data that's imputed from a neural network. And so you can take all kind of aggregated and non-linearly transformed predictions and still do valid inference. And so that's one extension. And I'd say, yeah, like 95% of economics papers, they're always aggregating the data that they impute from a neural network before they actually run their regression. And so we think this is probably how the framework will often be used in practice. Another extension that we'd like to that we look at briefly is, suppose you have some huge data set and the data of interest is a rare event. And so you have a social media data set and you only care about tweets on pesticides, but that's going to be a tiny fraction, and any topic is going to be a tiny fraction, almost any topic, maybe politics. It's the only topic that's not a small subset of any large kind of text data that you're using. And so when we create our annotated data, we need both positive and negative examples in it, right? So how do we do that? Typically how economists do that is to use a keyword method. So we're only going to label articles about economic policy uncertainty if they contain certain keywords. And the problem with that is you no longer, you're violating a strong overlap assumption, right? If your population of interest is all newspaper articles, you no longer have a representative labeled data set because you filter by a keyword before you label. And so the statistical literature would suggest using an importance sampling approach. And if I have time, I'll talk about this a little bit. And so this is all just to say, if you're interested in something that's effectively a rare event, there are still valid ways to be able to label data that will give you both positive and negative examples. All right. OK, so I want to just briefly relate this to the existing literature. I've already talked about this a bit. We build kind of most fundamentally on a much older literature from statistics and biostatistics on missing data. We build on a literature on semi-parametric inference. There's a literature on black box debiased AI. It's much more recent. It doesn't really kind of link back to this semi-parametric or missing data literature. So we're going to unite these literatures and also treat a variety of additional common empirical settings that come up in economics. I mean, the people by and large that wrote these papers were not economists. And so, of course, they weren't interested in our settings. We relate to a measurement error literature. At the end of the day, this is a measurement error problem. And this measurement error literature essentially builds upon the older missing data literature to think about measurement error. We relate to debiased machine learning. And then finally to a huge literature on causal inference. And I'll point out some places as I go through the framework where there are tie-ins to causal inference. All right, so now I want to introduce the framework, introduce the notation and the assumptions that are required for valid inference. And so we have unstructured data. I'm going to call that U. And that's too high dimensional, too complicated to use directly. We're going to impute the missing structured data M, which is low dimensional data that we can interpret, that we can use in our estimating equations. We observe the structured data through a process called annotation, but annotation is too costly to scale, and so we need to be able to impute missing structured data if we want to leverage our full sample, as opposed to having to rely on a really small sample that we can actually annotate by hand. And that's typically in a big data setting, that's going to be many orders of magnitude larger than what we can annotate by hand, right? So there's a huge benefit to being able to leverage that full sample. And in order to do that, we're going to use a deep neural network. That deep neural network, those parameters are not known. We have to estimate them. And so we denote that as mu hat. Yes.
A very naive question.
Yes.
So naively, I'm thinking, okay, if I have a manually labeled sample that is big enough to reliably debias, is it also big enough for me to just get a reliable estimate of the coefficient I wanted directly from running on just an annotated sample. The two must be related. If I only did 10 observations, they're probably too little to both de-bias, and if I consider that to be my random representative sample, I wouldn't get the right estimate. So in what sense there's a trade-off there?
I mean, maybe it's helpful when I actually kind of show you the expressions, but like, let's say you have only labeled 10 things. You know, your standard errors are going to be huge. So you can debias with 10 things, but the standard errors are going to depend on how many things you're debiasing with, right? Because you essentially, like, you have the term that you estimate on your huge sample, and that has, you know, that has uncertainty associated with it. If it's a huge sample, that uncertainty is going to be very small. And then you have term that you estimate, you know, on your labeled data, and the uncertainty of that is going to depend on how many observations you have. Although we find in practice that if, you know, it doesn't necessarily take a huge number, and, you know, in debiasing, you're going to combine kind of those two terms. And if they're really similar, you know, then that's fine. But I mean, I think that it's an empirical question that we haven't actually looked at. Although I think in the prediction-powered inference paper that I mentioned, you know, they do have estimates that look at that, and they find that your confidence intervals get tighter. Although I don't think they looked at that with kind of varying degrees of labeled data. And yeah, I mean, I do think like there was also, I think there's some other work on this as well, but I don't have that empirical example of like when it becomes like, well, your labeled sample's so large, there's no benefit to having like the full data set. But in principle, we could look at that, you know, what are the actual benefits of using the full sample? It's a good question. All right. Okay, so we're going to use a potential outcomes notation, which is what Rubin used as well, perhaps not surprisingly. So we have M, which is our missing structured data. We have an annotation indicator, which is A. And then M star is our ground truth. And so if we annotate it, we're able to observe the ground truth. And so I want to go through the assumptions that we need for valid inference. So first, we need a consistency of potential outcomes assumption, which just says that annotation status needs to be well defined. Either the data is annotated or not, and that tends to hold trivially. And the ground truth labels for any given instance depend only on its own annotation status and not on the annotation status of other instances. And so this is just basically like a consistency of potential outcomes assumption in causal inference. In causal inference, you need treatment to be well defined, and you need non-interference. That is, your treatment status doesn't depend on anybody else's treatment status. And so here it's the same thing, but think of treatment as being annotated. And you can achieve this in practice if you have like a well-defined procedure for annotating data, such that the procedure you apply to annotate isn't being primed like by the other, say, text or images that have already been annotated. All right, the core assumption is the missing at random assumption. So after adjusting for observables, which we denote as X, annotated and unannotated data are comparable in their ground truth values. And so this is analogous to a selection on observables assumption in causal inference. Obviously, it will hold trivially if the data are annotated at random, but they don't have to be annotated at random, including you could use some low-dimensional measure from the neural network, like distance and embedding space, to stratify what data you label, and that's fine, you know, as long as you have that X. Okay, the third assumption is that we have a known and bounded annotation score function. So that pi of X is just the probability that we annotate any given observation, given observables. And we need that to be bounded away from 0 and 1. And so this embeds what we would call strong overlap in causal inference. And the naming convention that we use of annotation score function mimics the usual causal inference terminology of a propensity score function. And so that this thing is known, we can relax that. It doesn't have to be known. I'll talk about that in a minute, although it's plausible that it's known if you, the researcher, are the one annotating data, because then kind of by definition it's a known function because you're the one that's doing it. The bounded part of it is important. So like if you don't, if you have zero probability of annotating certain instances, that's a violation of the strong overlap assumption. We can't know what the bias is for those instances if you don't annotate them. And so, when you talk about this to kind of econometricians, like some of them will say, well, wait a minute, you're working with this high-dimensional neural network, and in observational causal inference, strong overlap becomes less plausible as the dimension of the variable that grants unconfoundedness grows. But importantly here, the unstructured data, that's not what's giving us unconfoundedness. We have some measure x that's typically fairly low dimensional, so maybe we're oversampling observations from a given state or from a given industry. In that case, like the state or the industry would go into your x, and that's fairly low dimensional, and so kind of that's fine. And also it can be the case that x is a low dimensional measure of u. In fact, this is often the case when you're choosing what data to label, where you're using some embedding distance. You have a query, this article is about politics, and then you have the embeddings of your newspaper articles, and you oversample the ones near the query to get more of them that are positives. And again, that's fine because that x is fairly low dimensional. And so I wanted to make a note here. I mentioned this briefly earlier. Typically, the way that economists deal with kind of the issue of having severe class imbalance is they say, okay, I'm only going to label texts that have the keyword pesticide in them, and I'm going to kind of ignore everything else. And that's okay if you're only interested in texts that have the word pesticide. But if you're interested in all text and you're going to run your neural network over all text, then that is, again, going to be problematic because you have no idea how your neural network is doing on texts that do not contain that keyword. And intuitively, like we would expect the measurement error of a language model to be systematically correlated with the terms that appear in the text, right? And so we talk a bit more in the paper and point readers to references on how to deal with this sort of situation. All right, and the final assumption is mean squared error consistency of the imputation function. So intuitively, this condition just says that we need the expected square error of our estimator, so of our neural network, to go to 0 as the amount of data we train the estimator with goes to infinity. So in other words, the neural network is well specified, and this is very, very mild in the context of deep neural networks. So there's a recent theoretical work that has shown that certain classes of deep neural networks learn with gradient descent, including transformers, meet this condition. And just intuitively, if you trained your neural network on infinite data, it would give perfect predictions. Okay, then it's pretty weak in this context. All right, so as I mentioned, if you as the researcher are the one annotating your data, then your annotation function is known because you're the one who's doing it, right? And that's the easiest scenario to be in. Now, maybe you're in a scenario where somebody else annotated the data and you don't know kind of what that function is. That assumption can be relaxed. You can estimate it. Then you're going to have to make assumptions about the rate of convergence of the neural network. And I don't want to get into that, but there's technical points about this in the paper. I mean, I think the bigger problem is if you didn't label your data, do you have any way to know that that means missing at random is probably like the bigger problem than knowing what that annotation function is. And so, I'll concede that all of this gets more complicated if you're relying on somebody else's labeled data and they do not specify how they labeled it. You can estimate that, but did they use, is it a representative sample? Who knows? All right. And so I wanted to speak for a moment about what I mean by efficient inference. So a semi-parametrically efficient estimator achieves the lowest possible asymptotic variance of that estimator amongst all regular asymptotically linear estimators of that functional. So this is, this is essentially a fancy way of saying that that's going to attain the semi-parametric lower bound. Lower bounds are associated with efficient influence functions. There's a lot more technical discussions and proofs in the paper. I really don't want to get into this. I feel like if I talk too much about econometrics after lunch, I will lose everybody. But I want to just point out that, there's a lot of technical econometrics in the paper for anybody kind of with that background that's interested. I'm not an econometrician, and so it took me a lot of effort to understand this literature, but I tried really hard in writing the paper to make it as intelligible to people who know econometrics but are not econometricians as possible. All right, so that's efficiency. What do I mean by robustness? Well, in the context of semi-parametric inference, when we say that an estimator is robust, that means that we have constructed an estimator that relaxes the rate requirements for our first step estimates and multi-step procedures, right? And so in the context of deep neural networks, we have a multi-step procedure because first of all, you're using your neural network to impute your structured data. That's the first step. And then you're using that structured data to estimate some quantity of interest. And so the parameters from that neural network and kind of the language of the econometrics literature, those are nuisance parameters. You don't actually care about the 350 million parameters or 176 billion parameters in the neural network that's been estimated. But you need those. They matter. If those parameters are poorly estimated, you're going to get bad predictions. And so we call those nuisance parameters. In kind of this context, in the first step, you have the deep neural network that you're estimating. And then you also have your annotation function. And we're going to assume in the baseline framework that you don't have to estimate that annotation function because you annotated the data, so you know what it is. So robust estimators are designed to tolerate trade-offs and estimation error amongst the first step components while still maintaining asymptotic normality and root inconsistency. And so the basic idea is worse performance in one component of your first step estimation can be offset by better performance in another component. If we have two estimators, this is called double robustness, which is where the term double bias machine learning in the Chernozyukov sense comes from. And
to the robustness notion, presumably there are also inference questions as well. So in some sense, the machine learning is a first stage estimator, and there's going to be some standard error around or something like a standard error around the parameters of that model. And so just like in two-stage least squares, we're in the second stage, we need to kind of adjust the standard errors for the variance of the first stage. It seems like there's also potentially kind of a related inference point.
yes, and so we wouldn't know how to characterize that, and so that's why we're treating this as a black box. So you could, yes, if you knew how to characterize that, you might be able to get more efficient estimates out of there. And there is some work, but by some researchers who have taken like a topic model, which is a much kind of simpler model, and they characterize that bias, and then you can use that to debias. And so there's some work on that if you're using something simple kind of in the first step, but since we have no idea how to characterize that for a transformer, that's why we're treating this as a black box. And what you'll see is like the robustness is important here because we can have arbitrarily large bias in our estimation of the neural network, and that's okay because we're trading off that bias against the fact that we know our annotation function. We've annotated a representative sample, and we're going to use that to correct the bias. Now, if we have infinitely large bias and we try to correct it with our ground truth, our standard errors are going to be, large. That big sample is essentially telling us nothing, and at the end of the day, we only have our small annotated sample to go off of, right?
Even if it's unbiased, it seems like there's a kind of a inference question there, right? That there's an error in the machine learning model, and in some sense, I'm not taking. If I run my second stage regression and I just compute the usual standard errors, so I do MLS on my structured data, and I just compute the standard errors in the normal way, those standard errors are not going to sort of take into account that I've actually generated the data from a model that has implicitly.
Yes, but the debiasing is taking that into account. So debiasing, like one of the main things we'll see is it can really increase your standard errors. But you're doing that in essentially the way that the measurement error literature, right, does that. And that you're not trying to characterize what that bias is because you can't, because it's a transformer. Instead, you're just trying to empirically measure it and to adjust for that. And so that's exactly why we need double robustness here. If we didn't have double robustness, then we would have to worry about the convergence rate of the neural network, and we have no idea really like what that is, and it gets very complicated. But in this case, Mars is going to be weakly doubly robust. And kind of intuitively, the reason for that is we're able to have these very weak conditions, just what I showed you, the universal consistency. So we need the neural network to be well defined. If we trained it on infinite data, it would give perfect predictions, but that's all we need is universal consistency, because we have access to the most accurate possible first step estimator for the annotation function, which is the annotation function itself. We're able to correct for that bias by empirically observing it rather than having to characterize it in a closed form way. And by the way, we can get rid of universal consistency. So for instance, like if you use ChatGPT, you could put infinite data in there, and the error of it is not going to zero because you're not training it. You're just using it off the shelf. And then you won't have an efficient estimator, but it can still be unbiased. And in fact, most of the existing statistical literature on black box AI, they just assume you're doing that. You can just have arbitrary bias. In this, it's not going away asymptotically, but that's still okay, as long as you have this representative ground truth sample.
So in this context, is there any advantage from generating the annotated data on the large sample multiple times, for example, with slightly different models or with slightly different prompting? That seems like something that in the past this literature has not focused on, because it was either surveys of humans and they're not going to respond 50 times, or it was this is one data set we got and there is no ability to regenerate it. How would you incorporate that here?
Yeah, I think that's a great question. So you mean not for your ground truth data, like you still have a human label your ground truth data, but for your imputed data, you take like an ensemble of models essentially. Yeah, I mean, I think like we can definitely incorporate that, right? Because we know what the ensemble of models predicts. Again, it's a black box, and in that black box there can be an ensemble. Like we know what the ensemble predicts, and we know the truth. And so again, and like all of this framework, you could be using a keyword classifier. You know, the big data sample could be your RA who's doing maybe a poor job, and the ground truth is you doing it correctly, and you could debias your RA's predictions. You could use, like in that black box can be kind of anything that's an imperfect predictor. And yeah, I mean, whether ensembling is going to improve the prediction, I mean, I think it's at the end of the day, it's an empirical question. But I guess you can measure that. But yeah, certainly it's a possibility, but it's going to depend on the error structure of those models, and probably exactly what you do to ensemble them, like kind of how much they're going to help. But there is a big machine learning literature on ensembling. Okay, so how do we implement this? Well, first of all, as I stated before, we're going to need that your kind of target parameter would be identified if you didn't have this problem of missing structured data. So if the person who wrote the newspaper article had started by saying this is or this is not about economic policy uncertainty, you just had that, your parameter would be identified. Then you need to derive the efficient influence function. And I mean, in practice, you don't need to do this because we're going to derive them for you, okay? But I'm just stating, how you do this when you do it from scratch. We follow the method in Kennedy, 2023. There's essentially like 3 different ways to compute efficient influence functions, and they kind of have some different trade-offs in terms of how complicated they are and finite sample bias. And so we use kind of this approach, which is kind of used frequently in the literature. Then we need to construct the robust and efficient estimator. And we're going to do that by adding a one-step correction to a plug-in estimator that's based off the efficient influence function. Again, there's other ways to do this, but that's what we're going to do. These other ways would give you the same result in the end, but maybe they're a little bit more complicated. And we're trying to keep this straightforward. Okay, and so we're going to do steps 2 and 3 for you. And so we know what the estimator is, and you're going to see it's like super intuitive and kind of obvious, I guess, ex post if you're familiar with some of this literature, but we do all the derivations and proofs. And then so you have the estimator, you're going to do sample splitting for estimation, right? And this goes back to the question that was already asked. Your data that you're using for debiasing, that data is only used for debiasing. You're not using it to train your model, okay? And you're not using it to kind of estimate your, it's not part of your big unlabeled data set. You're just using that for debiasing. And it would be invalid if you use that data to train your model, because then obviously you'd be overfit and we'd have no idea what your bias was in the data that you didn't use to train the model. All right. So now I want to move on to the different estimators. And I think I'm going to go through this kind of quickly because we could spend time deriving them, but once you see the form that they take, it's really intuitive. And so again, I'm going to illustrate this on commonly used estimators. I'm going to start with descriptive means and then go on to other estimators. At the end of the day, all these estimators are very similar. Because these are essentially all mean functionals. IV, differences and differences, at the end of the day, these are all estimating means, and so the estimators are going to look pretty similar. This framework only applies to pathwise differentiable functions. This is kind of true more generally of these semi-parametric inference frameworks, and so that's just a caveat, and that's why we're doing RDD under local randomization. Okay, and as I said, all the estimators I'm going to show you are essentially estimating a mean of structured data. And this is, not horribly important from a practical standpoint. It's important from a technical standpoint because we're doing semi-parametric inference. We're not doing non-parametric inference because we're assuming that your annotation function, how you annotate the data, is known. If that was unknown, this would be fully non-parametric. And there's actually, in semi-parametric inference, there can be multiple efficient influence functions, and that can make deriving all of this really complicated, but we're able to prove that in the case of these mean functionals, the semi-parametric efficient influence function is the non-parametric efficient influence function, and that non-parametric efficient influence function is unique. And so that just simplifies all the proofs significantly. Intuitively, what is this saying? Well, this holds because if you label the data in a different but valid way, you would still get the same estimate. So nothing is relying on you labeling that exact set of text or images. As long as you have this representative sample, you could have labeled a different set of text or images and you'll still get, up to your confidence intervals the same estimate. And so that's why that holds. Okay, so I'm going to start out with the simplest possible example. We have some missing structured data. We've imputed that with a neural network. We want to estimate the mean. We can't do that on the truth m star because we don't observe that. Instead, we have this function mu that we're going to estimate with a neural network. And so we can derive the efficient influence function and derive the robust efficient one-step estimator. I want to kind of come to the next slide and write this. I'm going to write this in several different ways just to kind of make it more intuitive what this is saying. So the form that I wrote this in first, For those of you kind of more familiar with semi-parametric inference, you'll see that this is the augmented inverse propensity weighted estimator, which comes up a lot in causal inference. Let's kind of rearrange those terms a little bit, and we get the second expression. And you see there's a term that is essentially that mu hat term that's taking the mean of your data from your big sample, your predictions from your big sample. So that term A would be your estimate if you ignored the fact that you had imputed this data. So it's just the mean of, is this article about economic policy uncertainty, yes or no? Okay? And then the second term there is your correction term. And so you're taking the difference between your ground truth and what you predict, and averaging that, and it's inverse propensity weighted, right? Because you're weighting by the propensity the data with those observables are in your sample. But essentially, you're averaging that difference. And so basically, if there's a big difference between your ground truth and your prediction, the variance of this term is going to be really large. If you have a really small sample, the variance of this term is also going to be larger. And so what you're doing is essentially, maybe it's even easier to see this. I'm going to rewrite this again. And this comes from a paper by List et al., which he calls flexible regression adjustment. And here what you do is you take just the estimate in your ground truth, so what you labeled. And then you're going to adjust that with this adjustment term that leverages your full sample of data you imputed, but accounts for the differences between that and your ground truth. And so this is essentially has the same intuition as a linear regression adjustment. We adjust for those systematic differences between our large unlabeled sample and our small annotated ground truth sample, and use that approach. And so essentially at the end of the day, it's saying we have this ground truth estimate. We know that's identified, but we want to leverage our big sample. How do we combine these two things? Okay, you can think of that as just like, here's the estimate in our ground truth sample. Here's the estimate in our full big sample, and then we're just going to adjust that by the difference between our ground truth and our predictions, weighted by the propensity of that being in the sample. And our standard errors are going to account for the fact that that is measured with uncertainty. So that term, even if our N of our full sample is huge, and so let me go back. So the variance on this term, the first term is tiny. The variance on term B is going to be really big. If you have a terrible model, that term will be big because that difference is big. On the other hand, if you have a perfect model, this term goes to 0, right? And it's just like using the predictions from your huge sample, which is going to have, and maybe this kind of like goes back to your question about why not just use the small sample. Well, if the big sample is way, way bigger, you're going to get like essentially super tiny confidence intervals if your model is super accurate. You can really leverage that full data. All right.
I have a question.
Yes.
So in the last slide, for the annotation, the function is taking in the argument x, which is the covariates. But I would have thought that the annotation would want to take in the unstructured data and then annotate that. So I guess I'm having some difficulty understanding what exactly is x. Is x as simple as like, oh, is this a newspaper?
Okay, sorry. It's my fault for kind of maybe for going through this too quickly. And so x is essentially kind of the covariates that you observe. But then what's in parentheses here is x tilde, which is the combination of x and u. So that is your unstructured data going into that.
So, but couldn't that be like insanely high dimensional for like which data, for example?
It's insanely high dimensional, but what we need is that the neural network is universally consistent. So I think if we thought that neural networks couldn't handle the insanely high dimensional data, right, then they would be useless in some sense, right? And so we're assuming here that it's okay to feed high dimensional data into the neural. So mu hat is your neural network, right? And so kind of the basis for all of this is that you can feed high-dimensional unstructured data into a neural network and get something reasonable out of it. And that's a legitimate thing to do.
But then when you're doing the inverse propensity weighting, your probabilities could be very, very, very small, right? Like almost zero.
But we're not choosing what to annotate based on mu. We're only choosing what to annotate based on x. And so this goes back, where did I talk about this? To this idea of strong overlap. And so this annotation function, when we decide what to annotate, this is based on x and not on u. And x, we're assuming, is low dimensional. And you're absolutely right that if x was high dimensional, then strong overlap is implausible.
I see. So the strong overlap allows this estimate to be reasonable.
Exactly. So we're assuming x. So what gives you what makes your labels representative? What gives you unconfoundedness is not too high dimensional. I know there's a question about what that means in practice, like an empirical question. But yeah, that's very important. Sorry, as I get back to where we were. All right. I'll skip over. This is closely connected to debiased machine learning, but since that's a little bit tangential, I'll just kind of acknowledge that and and move on. Linear regression. And I should say, kind of in these examples, x is going to be, the data that we're imputing is going to be, it could be an outcome, or a treatment. I'm going to show one example. So in linear regression, your missing data is your outcome, but that could just as easily be something on the right-hand side, and everything would be fully analogous, which I think you'll see kind of intuitively as we go through this. So we're imputing our outcome with a neural network, and then we have a series of regressors, C. All right, and we want to do valid linear regression. I'm going to apply Frisch-Waugh. Again, I don't want to focus too much on the derivations, but we can form the efficient influence function. We see here that this is the estimator that we get. So if you remember standard linear regression, x prime x inverse, x prime y, that's essentially what this looks like. But remember y, the outcome is your missing structured data. So when you have x prime x inverse, x prime y, the y is that term in the square brackets, which is exactly the same term for mean estimation. Like, why is that? Well, at the end of the day, linear regression is also a form of mean estimation. Yeah.
In these regressions, are you putting the ML out, the output of the algorithm on the right-hand side or the left-hand side? And doesn't matter.
This is on the left-hand side here. And so that's why it's like in the y place. But if it was on the right-hand side, that's absolutely fine. And it would just be that you're doing that adjustment. Like C is just Frisch-Waugh, like the covariates. The adjustment would just be on whatever C, or it could be multiple C's, and that's fine too. It would just be on whatever C. And you'd just be doing the exact same adjustment, right? The same as you do for mean. That's it. It's just like your outcome, you just adjust it in the same way you adjust the mean. And I kind of tried to show this here. You can think about this as just a residualized regression that you run on like this pseudo outcome, which is just your kind of debiased y, your debiased outcome. And everything is going to take this exact same form. Before I get to that, I will say that one interesting thing that comes out of this is that the imputation function, your neural network, if you want efficient estimates, it's a function not just of your unstructured data that but also of your C, other control variables, relevant things in your regression, as long as they're not orthogonal to your outcome, which I think is kind of interesting. But in any case, I want to move on to linear IV. And so now here we have an instrumental variable Z, and we have our outcome Y. In this case, we're going to assume that our missing data that we're imputing is the treatment. Okay, again, it could be any of the variables in the regression, but for the sake of illustration, we'll say that it's the treatment. if we kind of skip forward to the expression that we derive, again, it's your standard IV coefficient, but now, like where the treatment would appear, you're adjusting it. So once again, it's like as if you're running this pseudo TSLS regression on your pseudo treatment, which is just the debiased, the debiased data that you've imputed, right? And so again, it looks like the exact same as the mean expression and the term where your treatment enters, but you're just doing that same debiasing that we talked about in mean estimation. Differences and differences. I know there's a lot of notation here that I'm going through quickly, but we essentially think of differences and differences as just, it's a difference in two means, right, at the end of the day. And so you can see it's the exact same, the exact same thing with some additional notation that I know I've gone through too quickly, but essentially you're taking the differences in these means and you're adjusting them for the fact that they are imputed with your neural network in exactly the same way, right, where you have the raw predictions from your neural network, and then you have this debiasing term that measures the difference between your neural network predictions and your ground truth, weighted by the propensity of that ground truth kind of being in your full sample. And RDD, again, now we're going to assume the missing data is the outcome. RDD is also a difference in means, right, at your threshold. And so again, the estimator looks, essentially similar. You're debiasing your outcomes for the imputation error. All right, I want to talk briefly about extensions, and then I do want to leave time to give some empirical examples. So the first thing I want to talk about is a world where you want to aggregate your predictions from the neural network, right? And so it's almost, in my experience, looking at a lot of papers, typically not the case that your regression is at the level of your text or images. Typically you're aggregating them. Often you're transforming them non-linearly. And so how do we deal with that? If you're transforming them linearly, it's pretty straightforward. The way that we deal with this in a much broader setting where you can have nonlinear transformations, interactions, is essentially very intuitive. So let's say you have some regressor in your model, x1. It could be multiple x's, but let's say it's x1 for simplicity. You're imputing that with a neural network, and then you're aggregating up and potentially transforming x, which is your treatment of interest. And what you can do is to just estimate the mean of x at whatever level you're aggregating with the Mars mean estimator that I showed you guys a few slides ago. And now that is unbiased, so that we know from what I showed you earlier that now you have an unbiased measure. Let's say you have an unbiased measure of economic policy uncertainty in the United States in 1997. And now you want to run regressions with the log of that, or with that interacted with something else. Well, now you have the unbiased estimator, and there's just one catch. It might be unbiased, but it still has classical measurement error, right? And so, if we go through, let me see if I can just pull this up again for the sake of, it's not going to work. If we go through and we have here this unbiased estimator. It's unbiased, your mean is unbiased, but there's still classical measurement error, right? So you can just plug in that unbiased measure of the mean, but you do need to adjust for the fact that there's classical measurement error in it, right? Doing that is very straightforward. So that goes back to the question from a while ago, kind of what about this survey literature, work by Deaton, et cetera. That literature was primarily assuming classical measurement error. And it's well known how you adjust for classical measurement error with GMM. I won't go into that now, but you can do this in Stata. And it's very simple, and it's been around since the 80s. Right, and so the basic idea, again, I know I'm going quickly through this, but I'm going to get to this real example in a minute. So let's say you want to measure economic policy uncertainty at different time periods in the United States by aggregating up millions of predictions from a neural network where you say, does this newspaper article talk about economic policy uncertainty? Well, the problem is we don't know the ground truth economic policy uncertainty in 1997 in the United States. That's a population level quantity. So we can't apply kind of standard debiasing, which assumes you know the ground truth. But instead what we're going to do is economic policy uncertainty in the US in 1997, which is kind of one of the variables you want to enter your regression. That's a mean, and we estimate that using the Mars mean expression. And now we have an estimate, an unbiased estimate of economic policy in the US in 1997, but it still has classical measurement error, so we can run our regression, but we just adjust for the classical measurement error. And why don't I'm going to skip over, maybe we can come back to this if we have time, but I'm going to skip over how to decide how to annotate data. I know that that's important, but that also opens a lot of questions, and because I want to get to the example. So I keep on talking about economic policy uncertainty because this is kind of an actual example that we use. So this is a 2016 paper. I'm sure everybody knows it. It has like 16,000 citations. And so the goal of this paper is they want to measure economic policy uncertainty. They do that by taking newspaper articles and predicting the share of articles each month that talk about policy uncertainty. So this is a 2016 paper, so they're not using a large language model, right? They're using a keyword search. And so what we're going to, they also have a really large ground truth sample, which is super helpful. So we're going to do several things. We're going to take their keyword search measure and we're going to debias that. And this is what I said earlier, that debiasing, it doesn't have to be a neural network. It can be any technology in that black box. So we're going to debias their keyword estimate. And then we're also going to take their validation sample and do sample splitting and use part of it to train a neural network and then use part of it for debiasing, right? And so we'll get a comparison between different estimates, which is what I have here. And so the pink is their, what appears in their paper. Economic policy uncertainty measured with keywords, ignoring the fact that this was imputed, right? Just treating it as the truth. The blue line is what happens if you use Longformer, which is a large language model. We use it because some of the texts are larger. If you use Longformer and treat that as the truth. And then the yellow line is you take their keyword measures and you debias them. This is, again, just using that expression that we looked at to debias a mean, because that's all economic policy uncertainty, and each year is just the mean over all the newspaper articles in that year. And then finally, the green line is debiasing the Longformer. I think there's a few things here to note. First of all, the confidence intervals are much tighter if you ignore the fact that these data were generated. Obviously, we could make the debiased estimates tighter by estimating better models or by having a larger annotation set. We're not doing that because we're using their annotated data. Okay, I don't want to be the one labeling economic policy uncertainty. I'm using their truth, but you do see it reflected kind of in the standard errors. Of course, the Longformer, the neural network, is more accurate than a keyword search, and so you see those standard errors are a bit tighter. And the bias is not huge, but you see a little bit of systematic downward bias relative to the debiased estimates. Okay, so now the primary reason for this exercise is that they want to run regressions with it. So this is one example regression. They're going to take the change in employment and regress it on the change in log economic policy uncertainty interacted with this intensity measure, and they have some other things in the regression. So this is a case where they've aggregated up the predictions, and then they're transforming them non-linearly, and they're interacting them. Fortunately, if we just estimate in each year exactly, we just take the estimates from this figure, and we account for the fact that this still has classical measurement error. It's the debiased ones, the yellow and green. They're unbiased now, but they still have the classical measurement error left. We account for that. This is what we get for that regression. And so the ones on the left-hand side, these are accounting for the fact that when we use these mean estimates in this regression, that they're still estimated with error. And so we're just using standard techniques to correct for classical measurement error. And you see the keyword measure and the neural network, the long-former measure, those are giving us kind of very similar point estimates. The long-former measure has a tighter confidence interval because it's a more accurate model. On the right-hand side, we're just taking these and plugging them in, kind of ignoring the fact that the blue and pink ones are biased, and that the orange and green ones, while unbiased, still have classical measurement error. So we just plug these estimates right here, like into this regression. And you can see here kind of very clearly in the gray and the pink, those are plugging in the de-biased estimates. You see the classical measurement error, right? It's attenuated, like no shock there. We know what classical measurement error in our right-hand side variables does. It attenuates. In this case, you happen to look at the blue and the green, which is just taking this, ignoring the fact that it's been, estimated with a neural network or with a keyword classifier and plugging it in. It actually looks really similar to the unbiased estimates that account for everything. Why is that? Well, that just happens to be a coincidence of this particular situation, because there's a classical component, right? There's a classical component and a non-classical component to those blue and pink estimates. And in this case, the classical component, it's attenuating it, but the non-classical component, this index is a bit biased down, so that's pulling it away from 0. Those two things happen to exactly cancel out, which is good. And I wouldn't, to be honest, want to show an example in this paper where I overturn somebody's results, because that's not like a fight I want to get into. So their results are great. You can believe their results. Of course, the confidence intervals are larger when you account for everything, but obviously not in every situation will the different components of your measurement error cancel out. I want to look in the last few minutes at kind of one other paper. This is a similar paper in that it was inspired by the EPU index, but they're looking at geopolitical risk. Instead, they're doing the same thing, measuring geopolitical risk in each year based on newspaper articles. They also use a keyword search, but we will take their audit data and train a classifier. So here you can see some really substantial sort of downward bias. The pink is their keywords. The blue is with a Distill Roberta, a neural network classifier. It's still downward bias, but not as much because the neural network is a bit better. And the green and the yellow are the bias corrected. And basically, in their ground truth audit sample, a very high share of articles during the world wars, and to a lesser extent September 11th, are talking about geopolitical risk. And their keyword classifier misses a lot of those, right? So it has good precision, but not very good recall. So that's going to lead to this substantial downward bias. And by the way, this is very common, especially with keyword classifiers. Language is complex. There's a lot of way to see things, so it's easier to get good precision than good recall. Now we're going to look at a regression. This regression, the regressing disaster rate on geopolitical risk. Okay, and geopolitical risk, this is just an annual time series. Okay, it's literally like the pink dots in this regression, right? That's what they're plugging in. So they're plugging in the pink ones, but I'm going to plug in these different ones, the same thing as for the EPU exercise. And you see here again, kind of something fairly similar. It doesn't make a huge amount of difference to adjust for the classical measurement error. You see some bias in their blue and green estimates. In this case, they really have very few observations because this is just an annual regression. So there's like sampling variance issues. Again, there's differences in the point estimates. They're not huge. Why is that? Well, clearly, the world wars were a very economically destructive period, and even with the biased indices, geopolitical risk goes up during the world wars, and that's what's driving these coefficients. But I think we can think of many examples where the effect might be more subtle, than the impact of world wars on the probability that there's an economic disaster. Which is essentially what this is picking up. So this is, again, just to say I've given you another example where it doesn't radically change our coefficients, but you could imagine other scenarios where the change might be bigger. It's still the case that the world wars are the main driver of economic disaster in this figure. And they have a lot of other regressions in their paper. I'm not saying this is the main one, but this is just what we chose to do. A quick note on design choices. This is varying the size of the annotated data. Obviously, this was your question. You get more precise as you annotate more data. Part of that's just you're getting a better model because you're splitting your annotated data between training and debiasing, but it also kind of helps with standard errors from the debiasing side. And so this is just the share of our sample. I think this is in the range of a couple of thousand articles labeled, so it's not a huge sample. This is varying the accuracy by using different neural network models that have varying degrees of accuracy, and the blue line is just using the truth. And again, you can see that as the model gets better, your standard errors get tighter. Although, kind of after a while, this is 85%, 90% accuracy. With modern BERT, it's getting like pretty close to the ground truth. But if you're down at it can make there's a big difference between 75% accuracy and 90% accuracy, which is, I think we could sit here and argue what's good enough, but here in this figure you see it, and 90% will give you tighter standard errors for sure than 75%. All right, so I think I am out of time, so just to kind of sum up, deep learning provides powerful tools for processing data. Hopefully you guys saw that in the first lecture this morning. But we do want to take into account that these models are not perfect, that neural networks measure things with error and incorporate that in a principled way. And we do that by essentially combining this new literature on black box AI and a much older literature on semi-parametric inference for missing data. And we apply this framework to a variety of common empirical scenarios and show that accounting for imputation bias is important and can influence both your point estimates and uncertainty quantification. All right, thank you.